is someone I hadn't seen from roughly 1980 until yesterday. At the high school in Baltimore that we both attended, there was a computer room that had a then very state-of-the-art computer the size of a refrigerator that probably had less processing power than my microwave oven today. And Marcus Ranum spent a lot more time than I did in that room, and it all paid off for him. He is credited with a number of innovations in firewalls, including building the first internet email server for the whitehouse.gov domain and intrusion detection systems. He has held leadership positions with a number of computer security companies, and Marcus's work has been cited in at least 15 published U.S. patents. Please welcome Marcus Ranum.
So, what I'd like to talk about today is based on, you've all heard the old saw about, you know, for want of a nail the shoe was lost, for want of the shoe, blah, blah, blah. What we're talking about is the consequences, the downstream consequences of a very small design mistake made by a farrier, or an implementation error, I should say, made by a farrier who was shoeing some knight's horse and screwed up and wound up destroying a country. It's a little difficult to make chains of causality like that that are extremely, closely specified. But what I'd like to do today is talk a little bit about some of the chains of causality that I have seen in some of the internet technologies that we're using all the time, and how what wasn't really a mistake, what was very, very small design decisions made by well-meaning engineers a long time ago has had some extremely unusual downstream effects. And then the other thing is I'd like to kind of do some, take the opportunity to see if I can actually teach about networking protocols sort of on the fly. Yeah, this is going to be, I wanted to challenge myself as well as you. So in the beginning of networking, you all remember the internet, and well, before the internet there was the ARPANET, and before the ARPANET there was a bunch of research computers that were stuck together in the early 1970s between MIT and some places in the government. And there was this piece of software called FTP, which stands for File Transfer Protocol. And File Transfer Protocol was the way all data got back and forth on these early networks. It was the only way you could get stuff. So it was how software distributions moved, and it was how email moved. Before there was another protocol, SMTP, the Simple Mail Transfer Protocol, that was invented because FTP really sucked as a way of getting mail back and forth. And as this FTP protocol really was one of the core capabilities of the purpose of the internet. It was basically FTP and Telnet, which was the remote login, to be able to remote job enter on a machine on the other side of a planet. So around 1976, FTP was written in 71, more or less. Around 1976, more or less, there was a thing called host-to-host protocol. And host-to-host protocol was later renamed NCP, which stood for Network Control Protocol. And NCP was later rewritten, re-implemented, and made better by another bunch of geeks. And they produced a thing called TCP/IP, which stands for Transmission Control Protocol, Internet Protocol. And that's the current set of protocols that run the internet as we know it today. There's a new set of protocols that have been in design for about 15 years, and they really haven't gotten off the mark. And one of the reasons they haven't gotten off the mark is because we have this gigantic installed base called the planet Earth, which is running the old version of TCP/IP. And you've got this interesting problem where when you've got everything being IP enabled, how do you upgrade the entire planet Earth? But that's another story for another day. So before TCP/IP existed, and everybody was using this NCP thing, FTP existed, and these were kind of like the primordial bacteria, if you will, that later blossomed on this evolutionary tree of life that gave us all the stuff that we're dealing today. Twitter is directly descended from these primordia. Okay, so network sockets are a thing I need to teach you about. A network socket is a software abstraction for how communications happen over the internet. And basically the way the socket looks, and I'm so glad my PowerPoints are working, because otherwise I'd be going, imagine a computer over here. But the way a network socket works is essentially it's an abstract rendezvous point for two things that want to exchange data. So here we have a server that's listening on a socket port. It basically says, I'm prepared to exchange data with somebody, I don't know who. And the client connects to the socket and transmits data and then disconnects. Almost all transactions that happen on networks happen in that mode. FTP is a little bit more complicated because it's trying to do more than just connect and disconnect. Sorry, I screwed that up. Okay. So the way FTP works is that the FTP server listens. It's prepared to serve files to people. It sits here and it listens on the socket port. The client connects to the socket. The client says, I would like to log in. Right? The server responds to the client saying, give me your password. The client then sends the password to the server. The client then creates its own socket port. And why would it do that? Well, I'll get to that in a second. And the client tells the server, transfer data to the socket port that I just created. The server then connects back to the client and transfers the data, and then the server says done, and then the client knows that it's done and drops the connection. The server, all very straightforward. There's going to be a quiz on this after I'm done. Now that's really silly, but what you're talking there is about 10 pages of code that was written by some geeks a long time ago, and they came up with this way of it working. Now, why did it do that strange thing where it makes the connection back to the client so that the data can be transmitted? You could think you just make a connection and you transmit the data. Well, as it happened, when host-to-host protocol was written, data could only go one direction on a socket. And when NCP was written, data could only go one direction on a socket. And when TCP/IP was written, people went, well, that sucks. Let's make it be able to take data back and forth on both directions on a socket. And that's exactly what happened. So the way TCP/IP works today, data goes back and forth both directions on a socket. It's very straightforward. But FTP still works the way FTP used to work. Now, why does this matter? The reason this matters is firewalls. FTP sort of inadvertently created the firewall because of this weird behavior where it does this callback from the server to the client. Because around 1986, 1987, existing router technology that you could get had the ability to screen traffic based on source and destination and other state information that was in the protocol, and we could have made it all work. We could have been able to sort of build a firewall-like thing just out of a router, except for this weird situation where a remote machine has to call back into our network from outside, and we really can't accept that connection because we don't know how to connect that connection with our original outgoing connection because they're separate. So I started coding firewalls, and some of my friends started coding firewalls, and I thought about torturing you by showing you what happens with all the sockets for this, but we don't have all day. But what basically happens is the client connects to the firewall, and the firewall does this hunky-monkey dance where it trades all the socket connections back and forth and moves the data back and forth between the client server, essentially acting like a man in the middle. It just runs back and forth. And it does access control the whole time. And this is pretty nasty to code, and that's one of the reasons why firewalls typically were a separate box, because it's nasty to code and you can't fix it, right? So we make it a separate machine so we can do all the hunky-monkey in the middle. And it turned out that there was a market for firewalls. The first firewall that I sold cost $175,000. Now, by the way, when you get your iPhone, it has a firewall in it. Everything that's on the networks nowadays has got a firewall in it. Your IP-enabled refrigerator has got a firewall in it. Well, because otherwise people would be inside your refrigerator owning, taking control of your ho-hos. So by 1994, the firewall industry, there were 3 different vendors selling firewalls. People went, hey, that's good. These guys are making money on this. Let's go into that too. You know, flipping burgers is much less fun than selling firewalls at $175,000 a pop. So by 1994, the firewall industry was $12 million in combined sales among 3 vendors. By 1997, there were about 15 vendors selling $100 million a year worth of firewalls. And nowadays, of course, firewalls have absorbed a whole lot more capabilities. They filter spam, they block porn, they do all kinds of other stuff because you've got this box here that really honestly doesn't do very much except shuffle data back and forth. So we may as well do spam blocking while we're in there. We may as well do porn blocking and whatever else we do. But today, people spend about $1 billion a year, give or take, on these kind of edge control technologies, right? That's an awful lot of money. And here's what's funny, It would have taken a good programmer about 2 hours to fix FTP in 1975. Right. I've talked to the guy who wrote FTP, and he said, well, you know, I've subsequently regretted the way I coded that. Of course, I wouldn't have had a wonderful 1990s if he had fixed it. But these hundreds of millions of dollars that were spent to fix a problem, and ironically, the problem is still here. Because we built the firewalls, no one ever had to fix FTP. And so the problem in FTP is still there. The firewalls are still there. People spend $1 billion a year or so on firewalls, and FTP is still there. So, right, for want of putting the nail in the right place, you've got $1 billion a year, and I won't say it's wasted, because it's a kind of a weird geek economic stimulus package. So let me tell you some more about sockets and socket programming. By the early 1990s, almost all of the implementations of major internet systems were running an operating system called Unix, which was based on some code from Berkeley, and we all used the same IP stack. An IP stack is the implementation of the TCP/IP protocol in your operating system. They were all about the same code base. And there was this thing called incoming connections. Incoming connections look sort of like this. It's a little hard to represent, but you've got a connection. The server sets up its socket, it's listening. A client wants to make a connection. And because of the statefulness in TCP, it actually takes a couple of communications back and forth to set the connection up and make sure that, you know, both sides really actually want to talk to each other. And until that happens, that incoming connection is put on what's called a partial socket table. And when the guys at Berkeley coded this, they were writing code. Jeff, by the way, the machines we were coding on had 4K of memory. And they were coding on machines that had about 1 megabyte of memory, which, you know, this little remote control probably has that. And so they didn't make these things very large. So they had this partial socket table, and they decided, because it was a good number, that they were going to pick 12 entries. And so that when you put this this socket about to happen on this partial socket table, you now have 11 left. You can see there's a possible problem here. And then once the connection was completed and the data starts flowing, it gets moved into the system socket table, and there were 2,000 or so entries on that. And these were all fixed. They were built into the operating system, and the only way to change them was to basically rebuild your operating system with different parameters, and that may have not make it work so well. So what does this mean? 1995, if you got 13 partial connections into a version of Berkeley Unix, it would crash and burn. By crash and burn, I mean the IP stack would stop responding because it didn't know what to do. Which one do I throw away? Which one do I accept? I'm just going to crash. You crash and you reboot, and then you don't have any socket connections. Well, what else started happening in a pretty big way around 1995, right? And you all know this, right? So, the World Wide Web. Now, here's what happens. Tim Berners-Lee, who was a very smart guy, and his friends, I guess I should say Sir Tim, they decided to make the HTTP protocol. HTTP is the Hypertext Transfer Protocol, which is what the World Wide Web moves over. Your browser talks HTTP. They wanted to make it stateless, and they made it stateless so each separate request used a separate connection, right? And so what would happen is when you went to index.html on some site is it would pull down index.html. That would have links to 5 GIFs, and then it would make 1, 2, 3, 4, 5 connections, each of which pulled down one of the GIFs, right? Bang, bang, bang. And then the browser assembles all this into a coherent-looking document. And it turns out there's a problem with this. You're making all of these connections. It's slow. You're doing a lot of back and forth protocol negotiation. And browser coders got this smart idea. Let's make 5 connections at once. We pull down index.html. It says we need to pull down 5 more GIFs. Let's open 5 connections, pull all the GIFs down in parallel. Wow, it's very snappy. So browsing got much snappier, and the servers got crushed because now the server was handling 6 connections instead of 1. So what happened? Well, the geeks fixed the connection limit problem in the server. So by 1996, very quickly, we had this evolutionary response from the server coders so that the servers could handle huge numbers of incoming connections. In other words, the problem that had made Tim Berners-Lee and his guys make HTTP stateless was no longer there. But let's talk about what happened because they put that nail in that particular location, right? Here's what wound up happening. 1997, internet commerce. Holy moly. It turns out that stateless is really bad if you're trying to do commerce, right? So, secure socket layer. You set up an encryption session with somebody. That's very expensive. You have to negotiate key settings and all kinds of fun things like that, and all this back and forth, and you're doing this for every connection and then throwing it away. That's why SSL is fairly expensive. Shopping carts, if you're buying something from Amazon, you don't want it to be stateless to the point where you fill your shopping cart and it empties it again every time you look away from your page. So Amazon suddenly has to start figuring out, well, how do I keep this state information, right? That's what cookies do. A cookie is a thing that your browser uses to identify a session to the server so the server can maintain your state for you as part of your login, right? So here's what's funny. The original specification for HTTP was stateless because of this funny little bug in Berkeley Unix, and the state keeps having to creep back in because the internet don't work so good without state. And now, all the software frameworks that geeks are working with, Ajax, Perl, Ruby on Rails, all these things, PHP, they've all got session management layers built into them in order to re-inject that state at a software layer. Now remember, TCP/IP keeps state. It's just not being used. Well, it's not being used to keep state, anyway. And so there's all these cookie tracking techniques, all these different techniques come up, and everybody does it a little bit differently, of course, right? Every programmer who wants to program in a different programming environment, if you're a PHP programmer, you have to learn how to use PHP session state tracking. If you're a Microsoft .NET programmer, you have to learn how to use .NET sessions tracking, blah, blah, blah. Everybody has to do it differently, and because everybody has to do it differently, of course they're going to do it wrong, but I'll get to that in a second. So then we have another consequence of this statelessness. Websites got big, websites got huge. You started to have server farms. A server farm is just 200 or whatever, however many servers you've got sitting out there. Well, you have to preserve the state, right? Because if I'm talking to a shopping cart on one server, I have to make sure my connections always go back to that server because that's where my shopping cart is stored. So even if there are 50 servers on Amazon or however many there are today, it's probably vastly more than that. But if there's 50, I have to go to the same one of those 50 all the time. Enter load balancers. A load balancer is a device, another box. It's running some software. It costs between $10,000 and $250,000, depending on the capacity of the site that you've got behind it. And what a load balancer does is exists to mitigate or to manage that state tracking process for the servers behind it. Again, because of this bug in Berkeley Unix that was fixed in 1996. So the bottom line here is that in order to re-achieve this capability that we already had, we have literally hundreds of thousands of coder hours being spent coding all these different state tracking, state maintenance things, buying all these expensive boxes to put in front of our networks and having to manage them and configure them, because I guess it might have taken those guys a few hours to fix HTTP. So we've got also security flaws. Because of these state management things, somebody might get it wrong, or a hacker figures out a way of injecting themselves in one of those. And as a consequence of the decision to make HTTP stateless and then now having all these layers of state management on top of it that sort of more or less work, we now have session hijacking attacks and cross-site scripting and SQL injection, HTML injection, all these different kinds of attacks that attack these different state tracking layers and allows a bad guy to inject themselves into the middle of that state tracking, which is very difficult to do with TCP, but is fairly easy to do with Ajax or PHP or .NET. Right. So here we go. We've basically had the problem solved by the time that we made it much worse. And you guys pay us for this. So really the point of this is there's some things that you can learn from looking at history. A lot of software engineers like to talk about biological models and computing, and they say, software evolves, and this is a dead end or this is not a dead end. Software does evolve, but the process of evolution, biological process of evolution, is intensely wasteful. And it's extremely unpleasant for the people who become dead ends. What's interesting with us for software is that those of us who are building software never really prune those dead ends. So software is this hugely connected enterprise where a small mistake over here can result in a multi-billion-dollar problem over there. right? And that's one thing to think about. Also, we could use a little intelligent design in the software field, right? Some sort of an omniscient overseer would be very nice. If you've got smart people who are brilliant about getting one thing done, but lazy about getting another thing done, and you've got the momentum of a 100 million user installed base behind you, you can get some really, really weird outcomes. Another observation about all of this is software is not your dog. You do not have to repay your software for a lifetime of faithful service like we've done with FTP. We've had FTP for 35, whatever it is, years now, right? We could have taken FTP out and just shot it. About 50, right? You can't do that with the dog that loves you, but you can do it with a piece of software because it's not alive, it doesn't care. And what's really funny is there are now about 15 protocols that exist to do the same thing as FTP and do it vastly better. But FTP is still there, and so are the firewalls. So what's really mattering about this, and the reason I wanted to talk about this, is because software has become a major cost driver in everything that we build. When you buy your cell phone, a significant chunk of your cell phone's cost is the software that makes the cell phone work. The clamshell case is the other part that's expensive. But you're actually paying for the software. Right? The software costs in an advanced state-of-the-art jet fighter nowadays almost cost as much as designing the airframe and the jet engines for it. So software is really a problem, and we're not doing it right. I guess that's really my point here. We need to be much, much less concerned with backwards compatibility. We kind of need an overall office of the take old software out and shoot it police who can come along and say, no, that's it, you can't use that anymore, it's dead, right? And we need to be much more aware of the downstream consequences of tiny little design decisions. Thank you.
Nice.